So when you look at uh, uh, an easy way to differentiate brittle and a ductile material is just looking at how it fails. So when you have a ductile material, you're going to have something like this, where it's going to be a soft material. So you have this reduction in area, which we call as necking, and at one point your part is going to fail. Even looking at B is also a ductile material, but you like when you compare A and B, definitely A is more very ductile. So typically, most of the metals are metals you look would the failure would resemble something like this. Okay, and coming to brittle material, it's so easy that it's just gonna fail. A good example is taking a glass. When you try to break it, it is just gonna fail, and you're never gonna see a cup or a cone like fracture, something as you see for ductile material. So whenever you see a material, and if it fails, just looking at the structure, you can know whether or not is it a ductile or a brittle material. So now that we know the difference between ductile and brittle material, let's talk more on ductile material, because we know brittle material is just gonna fail, and yeah, you won't see something like this cone shape or a necking happen. So ductile fracture, there's this three steps. You have this reduction in cross section. There's going to be some crack. The crack gets propagated, and at one point your part is going to fail. Okay, so this is what I had for brittle versus ductile material. With that said, this is another question I have for you guys. So you would have come across a plot like this, which is the stress strain plot, and this plot is specifically for a tensile load. So I would like you guys to answer if the stress strain plot is specific to ductile material, or is it a brittle material. So for which material do you think is the stress strain plot is ductile or brittle? Yes, you guys are right. It is a ductile material. An easy way to know it is just looking at this region, where, as I mentioned, only ductile material will see a reduction in area, and it will have some necking going on. So just looking at the plot, you can easily say whether it's a ductile or a brittle material. Okay, so one way to look at this is the reduction in the cross-section area and necking going on. So I have another plot just to show you a better picture of how each regions are. I'm not going to talk more on it, but just letting you know that initial shape is something like this, and that's where you start. And as you give your tensile loading, at one point you see there's reduction in the cross section, and it's gonna have necking, and that's where you have your stuff down here. One thing to note here is that is the maximum load your ductile material is going to take. So so that we define it as ultimate stress, ultimate stress or ultimate strength. And after that, since your cross section is being totally reduced, your stress value goes down, and at one point your part is going to fail. So just looking at this, you can definitely say that for a ductile material, your ultimate strength is always greater than your fracture strength because of necking going on. And please remember, this is for a tensile loading. Okay, so with that said, I'll go to the next one. I have a plot for a plot showing a stress strain plot for a tension test and compression test. So I've shown you guys a picture of how the loading would look like. With that said, one question I have for you guys is, does fracture occur first in tension or compression? Yes. And why do you think it is tension? What makes compression dominant? Before I ask that question, I'll answer you that fracture occurs first in tension. The answer is tension. But for people who have answered it's tension, why do you think it's tension? Why can't it be compression? What is the one main thing which makes to fracture and tension rather than compression? Mir and nickel, you guys were right. One is due to the crack propagation and due to reduction in cross section. So when you give a tensile load which is away, so you have this plate, you give a force away, and that's going to be this reduction in cross section necking happening, and at one point your part is going to fail. But whereas when you come to compression, it's the opposite phase. So you're trying to compress. There is no way that uh, maybe there's some crack develop, who knows, but uh, when you try to compress it, there's no way the crack is going to propagate. So it's going to take as much as load as possible. So there's no reduction in area, but here when you give, it's like something to do with increase in cross sectional area. So it takes as much as a load, but definitely at one point your part is going to fail. But when you just compare fracture in tension and compression, definitely compression is going to take much load before it fails. So that is what this slide signifies. When you look at the tensile plot, yes, you have the stress strain. The loading is somewhere down here, but for a same comparison, you see that uh, the load it takes to fail is more. That is what this plot signifies. Okay, I'll move on to the next one. Uh, yes, I just wanted to show you what I just talked in the previous slide.